the last topic that I will talk about in this polymer chemistry course. And these are very brief subject on the polyolefin synthesis using this catalyst. Okay? Catalyst is called right now as a Zieglar-Natta Catalyst, and we will talk about also the recent development of the catalyst system for polyolefin synthesis, which is called metallocene catalyst. And you will see how these catalyst system will change your stereochemistry of the polymer. In other words, you can make the isotactic or syntactic polypropylene out of this, the metallocene and the Zieglar-Natta catalyst. Before the invention of this Zieglar-Natta catalyst, we can only make the polyethylene with low density polyethylene, okay, low density polyethylene, which is called the LDPE. Okay, LDPE. This LDPE, low density polyethylene, was made because you have a lot of branches. Okay? If you think about the density of the polyethylene, the polyethylene is composed of a linear polymer, right? Linear polymer. But if the polyethylene has a branch graft, then the density is not as high as the linear polymer, right? So density will be lower if you have a branched system in your polymeric systems. Traditionally, in order to make this polyethylene, they used a very high pressure, such as over 100 bar, so that they have to use a very thick wall of the reactors, okay, in order to prevent any explosion of your reaction systems. But it's not very convenient in the industrial manufacturing of this polyethylene at the time, back in 40s and 50s. So the Ziegler and Natta and others developed some type of system where they can reduce the pressure of their reaction system. Okay? So if they use a catalyst, then they think that they could reduce the pressure from 100 bar to maybe less than 10 bar. So they produced high density polyethylene, meaning that you have a very linear system rather than branch system, okay, in your polymerization systems. We can have a LDPE, or is equal to high pressure polyethylene, HPP, by using the traditional system, whereas you can make the high density polyethylene or low pressure polyethylene, LPP, low pressure polyethylene, by using catalyst systems. So LDPE and HDPE have the polyethylene in the repeating unit of your polymeric systems, but density is quite different. Okay? So you have branch system in your LDPE. So it's a very flexible, very you can flow, you can make the very thick material, whereas HDPE, you can use a very thin HDPE film for your packaging purpose. When you go to the supermarket, they use a very thin packaging film, which can store your heavy items from your supermarkets, even the watermelon. Okay? And that film is made of HDPE rather than LDPE. Okay? HDPE can resist the heavy weight of your materials, whereas LDPE cannot. LDPE, if you make the packaging film of those that can be used in the supermarket, then maybe it will be much more flexible, so that the watermelon cannot be stored, cannot be taken out from the supermarket using the LDPE film. Okay? Anyway, those are the differences, and the LDPE or HDPE could be manufactured by using the catalyst system or not. Okay? And polypropylene, if you think about the polypropylene, you have three very different tactic systems, right? Tacticity was exemplified by this polypropylene, whereas the metal units in your side chain could be in the random way, which is called atactic, or could be in the same position, okay, same position, which is called the isotactic, or syndiotactic, alternatively, the MADEV. So the tacticity could be controlled by using the Natta system, the catalyst systems. So we will talk about the importance of this development of Ziegler and Natta. And Ziegler is a German chemist, whereas Natta is an Italian chemist. And from the invention of this Zieglar-Natta catalyst, they received the Nobel Prize in 1963. So although this has been a long, and old development of the polymeric systems, the Nobel laureate, Nobel Prize is not going to just very simple discoveries. So you think that the discovery of this Ziegler and Natta should have been very important in the early stages of the polypropylene and polyethylene developments. Therefore, traditionally we only can make the LDP, but from the invention we can make HDP and can make a very thin film, or you can control the tacticity in the polypropylene systems. So that was the subject of this chapter. Because of this invention, I think they can make the very high molecular weight the polymer, and they can make the syndiotactic or atactic syntactic polypropylene rather than atactic polypropylenes. Natta catalyst, which has been developed recently, is not the same as Ziegler-Natta system, but I just wanted to introduce Natta systems. Natta system is the combination of metal and leucine, and metal is embedded between these 5-membered pentadienyl cyclic rings. Okay? So this 5-membered cyclic ring is embedded between the metals, and this whole system is called Natta-leucine systems. Metals could vary from iron, titanium, and vanadium, and the metal can contain the chloride in their catalysis system as well. So they can abbreviate it as a ferrocene if the metal is ferrous. Titanocene contains the titanium. Vanadocene contains the vanadium as the catalyst systems. So those metals are very important for your synthesis of the polymer systems, which I will introduce to you to make the functional the polymer out of this polyethylene or polypropylenes. Now, if we go back to the Ziegler-Natta system, the Ziegler and Natta have received their Nobel Prize in 1963 as a consequences and development of an invention on the catalyst system, which was incepted by the end of 1953. And Natta, German chemist, the Italian chemist, received the Nobel Prize because of the stereospecific polymerization to the asymmetric autocatalytic synthesis of macromolecules, okay, which is related with the polypropylene. Okay. You see this picture is a tactic system, atactic, syntactic, and isotactic systems, which I have introduced to you early on of this class. Okay. And they won the Nobel Prize in 1963. the first Nobel Prize of this polymer, using the polymer system, I believe, is Staudinger. Staudinger received the Nobel Prize because of the macromolecular hypothesis, which was suggested in 1925-26 in the German Chemical Society, where I have introduced in the first week or second week of the polymer chemistry course. And he received the, he's not an experimentalist, but he was a theoretician, and he suggested that organic molecules may not be hydrogen bonded to gather together, but it could be covalent bonded. Okay? In other words, the polymeric system was suggested at the time, which is very shocking to all the organic chemists. So that after his suggestion in 1925 in German Chemical Society meeting, there's a lot of sensation, and as I told, the Carothers in the United States have tried to prove his concept of macromolecules in terms of the condensation polymerization in the United States at Harvard University, and finally became the product in DuPont. Whereas German chemists or British chemists try to develop the chain growth polymerization systems or addition polymerization systems and make the polyethylene, polypropylene, and vinyl polymerization reactions, so that there are two big, axes of the development of this whole polymer chemistry. So Staudinger received the Nobel Prize in 1953. 10 years later, this is the second group of the Nobel laureate in the polymer chemistry. Later on, the Paul J. Flory, Dr. Flory received the Nobel Prize in 1973 or 4, I believe. And he was also a theoretician rather than experimentalist. And he wrote a book in polymer chemistry back in 1956. At the time, he was a professor at Cornell University. And he visited Korea in, I believe, 1977. But anyway, those are the developments of the polymer and winners of the Nobel Prizes. Zieglar-Natta Catalyst uses. You can see the recent review about the Zieglar-Natta Catalyst and metallocene Catalyst. But anyway, you can see the olefin polymerization reactions. What it is that if you have metals, okay, metal M could be ferrous or titanium, vanadium, or if you have a polymeric chain, you can functionalize them. You can functionalize them so that vinyl monomer could be added to become a big molecules by using the some of the chemical mechanisms, such as beta hydrogen elimination, alkyl elimination, and transmetallization, so that you can form the new chain of the polymers. And this way, you can control any type of monomers. In other words, if you have a growing chain, if you change your R, you can change your composition of the copolymer systems, okay? Or you can change your stereochemistry, such as tacticity, or you can improve the activity of the polymerization reactions, and so on. So this is a very important development in the polymer chemistry. So if you go back to Zieglar-Natta Catalyst, I'll introduce you about the mechanism of what has been done for the last several decades, okay, on Zieglar-Natta Catalyst. Okay. Still, it's not very clear that there is a lot of theories about the Zieglar-Natta catalytic mechanisms. Okay? Although Ziegler and Natta developed the catalyst to make the HDP, okay, high density polyethylene, or controlling the tacticity, still the mechanism was not very clear at the time. Okay? But there is a lot of researchers working on about the mechanism of the catalytic systems. And I told you that there's a lot of theories. But I will just introduce you a couple of mechanisms. And this is not perfect mechanism, but this might be helpful for your understanding about what's going on about this Zieglar-Natta catalyst. Okay? Now, Ziegler uses a titanium tetrachloride as a catalyst. This titanium tetrachloride has a very different system than what we can think of organic molecules. In other words, titanium tetrachloride may have a one open position incorporating the vinyl group into your the titanium systems, and that's the assumption of their what is called the monometallic course mechanisms. And this assumption is that these 5 sites for chloride or open site could have the same the reactivity between this the open spaces. So if you have a titanium tetrachloride, then vinyl group will occupy this open space, so that you may have a vinyl group could be added into here. For example, if I have a titanium tetrachloride incorporated the catalyst and have a growing chain, how the propellant will be added is described here in these mechanisms. Okay. Now, first of all, if you have a titanium tetrachloride and growing chain, this vinyl group may have some sort of the transition state between the titanium and vinyl group, and form the tetragonal the transition states. Okay. Now this 4 axis is the chlorine. Okay. So you have 4 chlorines in the same plane, whereas the growing chain, carbon, and vinyl chain, the carbon-carbon, may have transition states. Okay. And this is not very stable, so it will be broken anyway. So assuming that you have a broken chain here, and may form the covalent bonds into one of the systems, so that way you can add this propylene monomer into your growing chains. However, there will be a flip over of this polymeric chain. In other words, open space versus this the growing chain may change their positions. What they call is a migration of these polymeric chains, which is a very funny story. I know it's very funny for you, but anyway, this way you can have the flip over of your syntactic polypropylene into the isotactic polypropylenes. Okay. And this is what they call the monometallic course mechanisms of the formation of isotactic polypropylene using titanium tetrachloride as a catalyst. This system, transition metal system, have several experimental evidences, and I do not want you to introduce those systems, and I'm not an expert in this as well, but I learned when I was a student at my grade school days. He was very expert in this area, and he's from Russia, in fact, suggested a lot of mechanisms of and evidences of this. And he introduced, this is one of the examples, and you can take a look at this type of a course mechanism in the textbook and in other references. And we can have a second mechanism called the bimetallic mechanism. And this is the monometallic because we use a one metal catalyst, such as a titanium tetrachloride. But the bimetallic mechanism is introduced in the next slide, where you have a titanium tetrachloride or titanium trichloride, whatever it is called. Titanium chloride may have a different crystalline structure. It could form a alpha crystalline structure or beta crystalline structure, depending upon their packing of their titaniums and the chlorines. So you have a different empty spaces in between. And I'm not an expert, as I said. The titanium, alpha titanium trichloride may have a one vacancy site, whereas beta titanium chloride may have two vacant sites or one vacant site. If you have a one vacancy site, then you can, they said that they can introduce the isotactic, whereas if you have two vacant sites, you may have atactic polypropylenes. Okay, so depending upon the crystalline structure of your titanium chloride, you can induce the tacticity of your final polypropylene polymer. Now, with that, the bimetallic system is the one that you have titanium chloride and aluminum chloride. Okay? Titanium chloride and aluminum chloride may form this tetragonal, complex system, and again, this is also a suggestion mechanism. Okay, what it is that you first form the tetragonal system, whereas vinyl group may add to this tetragonal systems and form hexagonal system. And one of these chain might be broken to form and stabilize into the tetragonal system rather than hexagonal systems. Okay? And this way you can add one of these monomer into your growing polymeric chains, just like what we have seen in the chain growth polymerization reactions. And this is the known mechanism called the bimetallic mechanisms. So in summary, propylene could be added into a growing chain of your titanium chloride and the polypropylene chains with the coarse mechanism, monometallic coarse mechanism, or bimetallic coarse mechanism, so that you form you can find the growing chain of your polypropylene in terms of the different tacticity. Okay, you can readily produce the isotactic polypropylene from the atactic polypropylene side of your the polymerization systems. So by controlling the crystalline structure of your catalyst systems, you can have isotactic polypropylenes. And this is I took this slide from the textbook, and you see you can see almost the same the words such as migration and so on in the textbook as well. So you start from the tetragonal and form the hexagonal system, and one of these chain will be broken into form the tetragonal. So your final the consequence might be the addition of your one monomeric units into your growing chain, and the second chain will be added as well as other chain growth polymerization systems. Polymerization rate might be different. I think I will have to skip this slide. And this is the second. I took it from the other textbook, and this is the same picture. You start from your open space. Okay, titanium tetrachloride. We may have open space, and may form the polyethylene or polypropylene. The ethylene or propylene units, and form the tetragonal system, and finally can form the hexagonals, and will be added into your polymerization systems and so on. The second, so that this way you can produce the high density polyethylene or isotactic propellants with high density. Although the density difference between the isotactic and atactic is not great, isotactic polypropylene may have a 0.94 grams per cubic centimeter versus the 0.9 grams per cubic centimeter of the density for the atactic polypropylenes. Okay? So the density difference may not be, great, but those very small difference in density will finally impact the property of your final polymers. This way, you can make a nice film. You can make a very strong film. This strong film, the strength of this film, or the density, high density polyethylene or high density propylene or isotactic propylene will be very important in the industrial the applications. If you wanted to make the very thin film made of polypropylene, these days you can make the thickness of this film by stretching or orientation with less than 10 micrometer. Less than 10 micrometer of thickness could be obtained by using isotactic polypropylene. Okay? 10 micrometer is only about 1/7 thickness of your hair. The thickness of your hair is about 70 micrometer, and 7 micrometer, for example, is about 1/10, only 10% of your thickness of your hair. This way, you can make a very thin film, and can be applied in the industry, in the electronic industries, electrical industries, and so on, in making the packaging films and condensers and so on. So the thickness of the film depended upon the strength of your polymer. The strength of your polymer depended upon the density of your polymer, the final polymer systems. The next that I can introduce is the paper about the mechanism of the propagation and chain transfer, and by using the metallocene type of the polymerization systems, you can make various types of the polymers. And this was introduced in Angewandte Chemie. Angewandte Chemie International Edition is a German chemical society journal. Interpretation of this journal is what? Applied Chemistry International, and this has a very high impact into your in chemicals the journals. And by using the different types of the metallocene systems, you can make the homopolymer with a very narrow molecular weight distribution, or you can make a block copolymer with a different color. You can make a copolymerization systems. You can have a grafted system or stop polymerization systems by using various types of catalyst systems. And this was a review paper on the living olefin polymerization systems, and what they call this as a living polymerization, because the catalyst represented as a red apple, or is live, so that you add your monomer systems, okay, into here. So it's more like an anionic polymerization system, which is called the living polymerization systems. And therefore, this was a very interesting system called the living polymerization systems, living olefin polymerization systems. You can also make the functional polypropylenes. Functional polypropylene is very important, because if you are using the polypropylene as packaging films, such as the packaging for your ramen, okay? If you think about the ramen, the packaging film, which is made of polypropylene, but you have to print some letters or colors on top of your polypropylenes. But polypropylene and ink system is quite different because polypropylene is very hydrophobic. There is no chemical bond. Okay, there is no chemical bond to make the hydrogen bonding with your ink system. Your ink system usually is two types of ink systems, which is organophilic or hydrophilic. Okay, organophilic or hydrophilic. Hydrophilic means aqueous systems. Okay, polypropylene does not have any bonds to incorporate the water, so it's not possible to make the hydrophilic ink coating on top of your polypropylenes. Okay, whereas if you have an organophilic system, yes, you can do that, but they may have a dot. It may have complete coating systems like what you can see in the laminate coating system. Okay? So you have to make some type of chemicals on top of your polypropylene so that those functional groups may have a bonding between the polypropylene and the ink systems. And this is what we call the functionalization. Functionalization could be applied not only to the polypropylene, but to our living systems as well. If you wanted to use your the biodegradable polymer as a suture, 수치는 수술용 봉합사라는 거, or any organic artificial organs, your body will recognize this exterior material coming from the outside of your body as I forgot the word in the biomedical system. Anyway, the external systems. Okay? So your body will attack those the outer systems, so that there is a lot of infections, a lot of the inflammations, 염증 반응 as well, so that your external system will not be existing unless you functionalize those exterior systems. So those suture or artificial organs needs to be functionalized, in that case biologically functional, in order to be used in your living systems. Anyway, those functionalization is very important, and this is one of the functionalization system of your polypropylenes. This polypropylene, if you have a polymerization systems and have the metallocene catalyst or Zieglar-Natta catalyst, whatever, then you can add the epoxy, you can add iodine, you can add protons and styrenes, and then functionalize with the aromatic rings, functionalize them with iodine, and finally you do with the diamines. You functionalize them with the hydroxyls and aldehyde, and finally you could functionalize them with hydroxyls and so on. So by using all those organic chemistry, then you can make the final functional groups attached at the end of your polypropylene growing chains. And this way, you can make a little bit of a hydrophilic. You can make a functional group, could be further reacted with other systems. This is what they call the end group functional polypropylenes. This way, you can make a functional polypropylene. You can make a hydrophilic polypropylene rather than hydrophobic polypropylenes. And this is one way of functionalization. Traditionally, what they will do to functionalize this polypropylene from the industry to be supplied for your ramen packaging film or other packaging system is that you first make the polypropylene, okay, extrusion. You first extrude your polypropylene and stretch them, okay. In the roller, they stretch them in the biaxial system. In the biaxial stretching is the one that you stretch with the roller in the axial system, and also stretch in the perpendicular to the directions. So they stretch in both directions, so that will make the very thin film, less than maybe 10 micrometer, okay, and then wrap the system. And this wrapped polypropylene or extruded polypropylene is hydrophobic. But before shipping to ramen, packaging film or coating the company, what they will do is that they expose this polypropylene with corona discharge systems. Corona discharge system. In other words, the high electrical energy is applied to the polypropylene. So you see the glow of the blue, blue color, the electrical charges on top of your polypropylene. And after this corona discharge system, the oxygen from your air will be the foam will be reacted with the polypropylene system. So instead of CH2 CH3 system, you have on top of your surface of your final film, you form peroxide system, COOH, okay, COOH or COH, whatever, systems, and by using this corona discharge system, then you can print your any ink systems. Okay? So this way, this is a very convenient way of industrial application of functionalization of polypropylenes, but very complex functional system could be made from the producer of the polypropylenes. Right now, we have manufacturers of the polypropylenes. One of the oldest manufacturer is 대한유화. 대한유화. I don't know what the English name of the 대한유화, but Korean petrochemical company or something. I'm not sure the exact English name, but 대한유화 produces the first polypropylene and polyethylene in Ulsan, and the owner of this 대한유화 is from Hanyang University, the class of 1978. He's not an engineer, but he's from law school, the College of Law, and he's the CEO of this 대한유화. And this was the first company producing these polypropylene and polyethylene, and they produce the high quality polypropylenes, and perhaps the other makers right now producing this polypropylene and polyethylene is Samsung, Total, and Hyundai, and LG, and other major producers are producing this polyethylene polypropylenes. So we in Korea produce the very large amount of this polypropylene and polyethylenes, but not using this chemistry. Okay? This is still in the development of the stages, but they produce high quality polypropylene to the film maker, and the 대한유화 supply the film the PP to film makers such as Samyang Chemical or Hwasun and so on, and those companies produce the films, and before shipping, they post the treatment of this produced films, and other companies like Samyang Ramen and others will printing their ink and packaging the whatever the food or whatever the product they will use. Okay, we can also functionalize these polymerase systems, and by using this polymerization systems, you can make the copolymer systems, block copolymer systems, or you can make the other polymerization systems. Block copolymer, as you have already seen, was and I have introduced to you, very difficult to make, right? Okay, very difficult to make. But using this metallocene system, because it's a living olefin polymerization systems, you can just add second monomers, okay? Second monomers on top of the first monometic systems. And by using this system, you can have polypropylene block PMMA, which is not very easy, okay? You can make the polypropylene block EPL, the ethylene propylene rubber system, and PP. You can make a PP and PS block copolymer. You can make a PP and polytetrahydrofuran block copolymer systems, and so that you can modify your property of your polymer systems. Polypropylene itself has a low glass transition temperature, but this polystyrene is glassy, okay? And this EPL is rubbery. So you can see, the very, very interesting property of your final block copolymer systems. And this way, you can produce very interesting polymerization systems. And one of the important aspects is that you can produce the exact, the amount of the molecular weight or the distribution of the molecular weights. Okay? Molecular weight distribution is very close to 1, which means that it has a very sharp molecular weight distributions. And I told you that it's very interesting, very important, and they can produce these interesting polymerization systems. And this is one example which was introduced in the review paper back in about 10 years ago. So, so far I have introduced to you the catalytic system to make the polyethylene, polypropylene, and other block copolymer systems using the Zieglar-Natta Catalyst and the recent development in the metallocene catalyst. And by using these catalytic systems, you can produce the high density and very distinct the polymers of interest. And also, using the recent development of metallocene catalyst, you can produce the functionalized PP and PE and other block copolymer systems, and so on. And this is what we call the coordination polymerizations. Coordination polymerization system. 배위 중합이라고 해요. 우리가 이제 coordination polymerization system. So I introduced to you in chapter 12 about the coordination polymerization systems, because coordination means that you may have metals in your catalytic systems. So the coordinate between metal and the organics will be the mechanism for producing the very important polymers. Right? And these polyethylene, polypropylenes are the major product of the polymer systems out of the petrochemicals industry. And in Korea, we are perhaps the number 3 or number 4 country in the world producing this PE and PP. And you see the quality and the functionalization should have been very important, because you have a follower okay, China, and they expand a lot of their capacity to produce the P and PP, and also the Middle East countries, as well as the Southeast Asian countries are producing their own petrochemical factories, and so that depending upon the supply and the demands, the price of this petrochemical will be fluctuating, and petrochemical industry, particularly, is not very small industry, but it's a very it's not a labor-intensive industry, but it's a capital-intensive industry. So that once you invest your capitals to your the petrochemicals, you expect to have a lot of incomes later, of course. But it depends upon the markets and the prices of the chemicals. So from 1970s, 60s and 70s, the Korea put a lot of efforts into producing this P and PP. And as I said, we are the one of the leaders of producing this petrochemical polymers. Yes. Any questions about this, the coordination polymers? Everything's clear? We're almost the end of the class right now, and the remaining subject that I will cover is that I'll introduce to you about the polymerization processes in chapter 13, where you can, I think we can go very quickly about this subject. And finally, I will introduce in chapter 14 about the functionalization of these polymers, or application of the polymers in the real world. Okay, and from my perspectives, from my viewpoints, I just would like to introduce some applications, not all, but some applications of the polymers into the real world. Could be in the chapter 14. So if you don't have any question, then I can proceed with the chapter 13, which is about the polymerization processes. Well, so far I have talked to you about the mechanism of the polymerizations. I told you about the step cross polymerization, and chain cross polymerization, addition or condensation, radical, ionic polymerization, and those were, about the mechanisms, in fact. And I have asked you to know about the structure of your monomer systems and polymer systems, of course. So how you can name your polymers. But that doesn't mean that you can produce the polymer. Okay? You have known. You have understood about the polymerization mechanisms, but the making the polymer is a little different story, okay? A little bit of a different story. So in this chapter, I just wanted to introduce you how you can make the polymers in real experimental scales. Okay? In other words, you may proceed the polymerization with the monomer and initiator, which are the very most important, two very important, the chemicals, and you may have a solvent in addition to those two systems, or not, okay? Depending upon your polymerization systems. You could proceed with the bulk polymerization or solution polymerization systems, or you can add the surfactants in your polymerization systems or not. So depending upon what is the other additives into your polymerization systems, final consequence of your polymer and molecular weight might be different. So in this chapter, I just wanted to show you the technical aspect of polymerization systems. Okay. So in the polymerization system, it is classified as 4 very important polymerization systems. We can have bulk polymerization, solution polymerization, and those 2 systems are called the homogeneous polymerization systems, whereas you may have a heterogeneous polymerization called the suspension and emulsion polymerization systems. Heterogeneous and homogeneous means that heterogeneous means you have other different from your polymers. Polymer is usually composed of monomeric units. Okay, when I write down ethylene, polyethylene, structure of this polyethylene, okay, then I just skip the catalyst systems, right? As you've already seen in the red apples, what I call the red apples, as a metallocene or a Zieglar-Natta, whatever, you should have a catalyst at the end of your chain, of course. But I just skip that structure, right? But you may have a small amount of your catalytic systems. It could be removed or could remain as it is, okay? Depending upon what kind of catalyst that you use. So, although I'm writing the polymer structure by using monomer systems, you have other additives, other chemicals. An essential part should be catalyst, right? Catalyst. And may have a solvent, but solvent should be removed anyway, right? Solvent should be removed. Or could add surfactants. Surfactants is nothing to do with the polymer systems. Surfactants is just aiding, aid or assist in polymerization systems. And those other systems, other than catalyst, is regarded as external system, external chemical components. And if you add the external chemical components, we call that as heterogeneous polymerization systems. Whereas if you do not have any exterior the chemicals, we call it as homogeneous systems. So, bulk polymerization system contains only monomer and initiator. Monomer could be in the liquid form, of course, in the liquid form, and the initiator, so that you can increase your the temperature and reaction proceed with only the monomer and initiators. Now, usually the polymerization system is regarded as exothermic reaction, so that you induce a lot of heats from your reaction systems. And one of the disadvantages of this bulk system is that how to control your temperature of your reaction systems. Because if you exert a lot of heats, okay, a lot of heats, then you have to absorb your heat anyway in order to prevent any explosion from your reaction systems, right? So controlling temperature, particularly reaction temperature, is one of the big issue in bulk polymerization systems, but it's possible. Yes, it's possible. Solution polymerization system is the one that you have a monomer, initiator, and solvent. Solvent could be, put it into your polymerization systems, but you see there is advantages and disadvantages, of course. Advantages is that it's easy to control the temperature because you have other liquids in your polymerization systems, so that solvent may have a heat capacity to absorb the heat, and it could be dissipating, and temperature control might be easier than the bulk system, because the temperature rise may not be not very highly abrupt, as in the case of bulk. In the case of bulk, you have a very rapid increase in the temperature all of a sudden, so there might be an explosion. But in the solution polymerization systems, well, it's slowly increasing, so that you can have a jacket around the reactor, so that you can control the temperatures of your polymerization systems. Okay, that's the advantages. What about the disadvantage of this solution polymerization systems? Efficiency. Efficiency might be an issue. What do you mean by efficiency? Polymerization efficiency? Yes, in terms of, you learned about the chain transfer to solvent, right? Chain transfer to solvent. Chain transfer could be applied to the chain transfer agent, intentional chain transfer agent addition, could induce the chain transfer reaction, or chain transfer to solvent. Therefore, the efficiency might be dropped. That's correct. What's the next disadvantage of this, the solvent system or solution systems? Well, do you need to discard this solvent, or do you need to recover those solvent systems and reuse them? We have to recover. We have to recover this solvent. Okay? We have to recover this solvent. Otherwise, it's too costly to manufacture this polymer. We have to recover those solvent. We cannot evaporate the solvent to the air, right? Because of the environmental issues and others. So we have to reuse them. We have to recover and reuse them. Otherwise, there might be a cost issue, an environmental issue, right? We cannot discard it to the air. We cannot discard it to the waste systems, right? Because of environmental issues and others. Therefore, we have to reuse them. We have to recover them within an environmental limit, and that's very difficult. That's very difficult. That's not easy systems. Okay? But recovering of those solvent by using any chemical engineering processes, separation, purification, the extraction, all those chemical processes should be applied to recover those solvent systems. And that's costly, of course, but it's possible, right? It's possible. And the third issue might be that although you recover most of the solvents, some solvents might be included in your polymer systems, right? Although you dry the polymers, but residual solvent content might be an issue in the polymer systems. So you have to recover, as many as possible. As much as possible, the solvent is an issue, as well as the residual solvents should be disadvantage of the solution polymerization systems. Suspension and emulsion, they use the surfactants or soap detergents. Okay, surfactants, detergents, or soap. Did you learn about the colloid chemistry? No. The detergents or surfactants, okay, will make the droplets I think I have a picture. So I will introduce about the details about the suspension and emulsion systems. You have a larger droplets and smaller droplets. So that within the droplets, such as droplets with the milk or detergents, so within the droplets, the polymerization is proceeded within the droplets. So this is what they call suspension or emulsion systems. The purity of the final product is an issue as well in this heterogeneous system. You have a milky polymers, milky polymer. Let me see. When I think about the milky polymer, do you know the Elmer glue? 이 벽지 바를 때 왜 이렇게 그 바르는 풀 같은 거 있어요? Glue, where you apply those white milky glue, you buy them, but a long time ago we use the starch. We use the rice soup or something to apply for your starch glue on the backside of your wallpaper and put it into to your walls. But these days, I think you can buy the white milky glue, okay, that is made of polyvinyl acetate. Polyvinyl acetate made from emulsion polymerization systems. This emulsion, the polyvinyl acetate emulsion contains not only polyvinyl acetate, structure of the polyvinyl acetate, and catalyst and detergents. Because of this detergent, what we call is emulsion. Okay? So those white milky polymer system is one of the representative example of the emulsion polymerization systems. So let's go through with each of the bulk to the emulsion polymerization systems. So bulk polymerization uses only monomer initiator. It's very cost effective, chemically pure, but the viscosity is an issue. Viscosity increases very abruptly, and very difficult to control the temperature as well. Example might be the mass production of this PVC, PMMA, and GPPS. What do you think about this GPPS? This is abbreviation, right? What do you think about the abbreviation of this GPPS? 무슨 뜻 같아요, GPPS? The reason that I'm asking you is that you will see a lot of those abbreviations in the catalogs of your company. Okay? HIPS, 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 ABS, GPPS, HDP, LDP, stuff like that. You see a lot of those abbreviations. Usually, when you take a look at these abbreviations, look at the final words. PS means what? Polystyrene, right? This is polystyrene. Polystyrene. What do you think about this GP? Guess. General purpose. General purpose. Polystyrene. Okay, GPPS. HIPS. HIPS is HIPS. Polystyrene, of course, right? But high impact strength. High impact strength. Impact. Right? I think the company uses a lot of abbreviation, just like what you're doing in your conversations. So HIPS is a kind of the blend or copolymer with polystyrene and what? Polystyrene is a glassy polymer, so it's very easy to be broken, glassy. If the polymer can resist the impact, okay, resist the impact, not to be broken upon applying for the impact. You should observe the impacts, and should add the rubbers into your polymerase systems to have a high impact strength. high impact strength가 되려면 어떻게 해요? 고무 같은 걸 집어넣어야 돼요. 고무는 임팩트에 대해서 강하잖아요. 그죠? 고무는 임팩트에 강하니까, 그러니까 임팩트에 대해서 강하게 하려고 그러면 고무를 집어넣어야 돼요, 무조건. 그래서 polystyrene with the rubbery part, such as a butadiene, small amount of butadiene will be a HIP systems. So if you go to a company producing your polymer, or if you're using a polymer, for your energy application and others, you have to take a look at their catalogs, and there's a lot of abbreviations. Okay? A lot of abbreviations. I don't know what it is. LDPE, VLDP. What do you think about the VLDP? That's correct. Very low, very low density polyethylene, stuff like that. So you have a VVLDP, just like a VVIP, not VIP itself. But anyway, you see a lot of those applications in the catalogs, and this is one of the examples. I think I have to stop because I have a class at 10:30 as well. So we can continue on our discussion about polymerization systems on Friday. Okay, so I'll see you on Friday.